Welcome to another episode of Code for Thought ByteSized RSE, sponsored by the Universe HPC program. Our theme for this month's ByteSized RSE is testing, but not testing as you know it, like unit testing, integration testing, or system testing. What I'm going to cover in the next few minutes is a different concept altogether, property-based testing. And to help with that, I invited two guests. One is Duncan McGregor, who I've worked with a long time ago, and the other one is Nicholas Del Grosso, and you'll hear from them both a little bit later. But let's go back to property-based testing now. Compared with other testing principles like unit testing, the origins of which may be dated back to the beginnings of programming, property-based testing is a relative newcomer. It started originally with a programming language called Haskell. Haskell, for those of you who are not familiar with it, is a language named after an American mathematician and logician, Haskell Brooks Curry, and it appeared at the beginning of the 1990s. Haskell follows the so-called functional programming paradigm, and for those of you interested in what that is, I include a link in the episode notes. But I don't want to go on too much about Haskell and functional programming, except that for Haskell there is a library called QuickCheck, which was developed by Colin Klesson and John Hughes, both computer scientists. QuickCheck is, and I'm quoting from the manual, a library for random testing of program properties. The programmer provides a specification of the program in the form of properties, which functions should satisfy, and QuickCheck then tests that the properties hold in a large number of randomly generated cases. The first release of that apparently was in 1999, which is quite some time ago. So why am I saying that it's relatively new? Because it wasn't until quite a bit later that the principle of testing used in QuickCheck, that is, property-based testing, were ported to other languages and popularized to a wider community. In fact, it was in 2013 that an engineer called David McIver started working on a property-based testing library for the Python programming language, which he called Hypothesis. He released version 1 of the library in 2015, and since then many upgrades followed, and we are now being April 2024, at version 6. Python, by the way, isn't the only programming language the concept of property-based testing was ported to. There are libraries for many other languages like Go, C, JavaScript, and, as Duncan will tell us in a minute, for Kotlin and Java as well. So what is property-based testing, and how is it different from the concepts like unit testing? Let me hand over to Duncan McGregor now. As I said, Duncan and I have worked together for a few years a long time ago. Duncan is a highly experienced software engineer, teacher, and mentor. Back in the days, he was the one who introduced me to extreme programming and the concept of test-driven development, concepts that in the early 2000s were still new and fresh. I found Duncan recently online, where he provides online training for Kotlin on his YouTube channel, Refactoring to Kotlin. In one episode, he talked about property-based testing, and what a great opportunity I thought to catch up with him and get his view on his testing approach. In fact, this was the first time we met after we worked together nearly 20 years ago. So here's Duncan. Hello, Duncan. Thanks very much for your time today.
Peter, it's lovely to see you again.
Yeah, indeed, exactly. It's been quite a long time and a long time no see, and we instantly recognized each other, which is even more amazing.
Given that we're the only people on the call, that wasn't hard, but yeah.
But we like a challenge, don't we? Anyway, Duncan, I know you very well, but the listeners probably, some of the listeners may, because they may listen to your YouTube channel or watch it, but maybe you can quickly introduce yourself.
Hello, I'm Duncan McGregor. I think I was originally a physicist, so I was trained as a physicist in the 80s, then ended up working for the UK Ministry of Defence, largely on computing projects, left them after a while, and really have been a jobbing computer programmer, I suppose, for many, many years, too many years. I sort of ended up on the Java virtual machine, so programming in Java, then Scala, and these days Kotlin largely. I think we met at Sony in their laboratory in Basingstoke.
We did. Yeah.
I don't even remember what that project was about, but I must have been doing Java, and I don't know whether you were at the time.
It was Java. It was Java, and it was the material exchange format.
Yes. MXF, those
The
fun
MXF.
days.
Yeah, but this is not a horror show. This is sort of something to tell people meaningful. Okay, we're talking about testing because you've done a lot of work, apart from software development, but testing is a crucial part of software development, and you've done a lot of work in that space. But today we're not going to talk about testing in general. We're talking about a very particular part of it, which is property-based testing. And maybe you can give us a quick overview what that is, and perhaps even where it comes from.
Yes, let's try. So my background was largely test-driven development, so extreme programming originally. And in those cases, we write tests to push the software in a sort of certain direction. We say, it doesn't do this thing, let's write a test for something it doesn't do yet. And then we will add the functionality to make it pass that test. And then we'll say, okay, that one's done. Now let's write another test for something it doesn't do. And that's a nice way of developing software, but it really relies on writing good examples and having an idea of what those examples are going to be. And really, we're only testing it for the examples that we write a test for.
Right. Could you give an example?
Yeah. So let's say very simplest, let's say we wanted to write a test for the function that takes the length of a string.
Mm-hmm.
So we might say, well, if I have an empty string, then I'll assert equals that the length of an empty string is 0. And I might assert equals that the length of banana is 6, because bananas are my favorite strings. But the question then is, well, what about all those other strings? Like 2 examples, maybe 3 or 4 might be enough for a simple case, but maybe we've got Unicode and we're worried about Unicode. Like, is it reporting the number of bytes or is it reporting the number of characters and so on? And so we might want to generate examples rather than having to dream them up ourselves.
Okay.
And so I think originally the sort of Haskell programmers came up with this idea of testing by saying these are properties of a function, of a software system, and that I will write down what the properties are, and then the software will throw examples at our program, at the thing under subject under test, if you like, and try and disprove the properties that we said exist.
Right. Is it doing that by picking things randomly? Is that how it works?
I mean, yes. I mean, there's random and there's random. So if, say, we had, obviously length of the string is not very interesting, but say we have a function that takes, I don't know what, a string and 2 numbers and does something, who knows what with those things, right? We can write properties to say, given this number and that number and this string, this is what it should look like. Or maybe a property would just be, it always gives a result, or in this case, it always fails, with properties like this. Now, what sort of input should we throw at it? Well, we might, as programmers, think to throw an empty string at it. But if we didn't, empty strings aren't very random. I mean, they're probably the least random of all strings. But we might expect our property-based testing system to at least throw one empty string at our software just to see what happened, to see whether it matched that. And the same sort of thing with integers, for example. If we throw a number at something, then 0 is probably an interesting number. But 0 comes up very infrequently if we're just throwing random things at it. So we have generators, and generators are the things that generate the inputs to our functions. And they are sort of a combination generally of random and then some pretty specific things that are likely to be awkward to us. So we might expect 0 to come up as an integer. We might expect a maximum minimum values of integer to come up, but then we might expect 37 apparently is the most random integer that people can think of. So we might expect 37.
Okay. Right. I thought it was 42, but never mind. That's all very good. But is it then replacing unit testing?
I mean, yes and no. So we have to ask the question, like, what are our tests for? As a test-driven developer, we start from our tests are to help us generate the code. That if we have to write unit tests, then our code will tend to be better structured than if we didn't have to. But after that, tests do other things for us. They are documentation for what we expect to happen, given this example. So, for example, our customers might be able to look at them and go, oh, yes, that is or isn't what I expected this to do. So that's the thing that tests can do for us. And they are also regression. So they allow us to know that it worked once and it's still working, providing we actually run the tests. And generally, we might think that we can predict when something's going to break, but often things break because I change the behavior of something that the thing that I'm actually testing relied on. So that regression is a useful part of our tests. Property-based testing, I think, is more useful it's useful because it will throw examples at things that we might have forgotten to do.
Yeah, like edge cases or
the edge cases and so on. And from that perspective, personally, I think that like software developers have to be lucky and optimistic. We make progress by being lucky and optimistic, but that sometimes means that we forget to test something with an empty list or an empty string, or a string with Unicode characters in it, or -1 for numbers and these sort of things. So it's useful for those things. And I think it's also useful for the combinations of things that we might forget. And it's also very useful for things where actually the behavior is, what should we say, difficult to specify in other ways for lots of options. So I was recently writing some example on my YouTube channel about 10-pin bowling.
Right.
And using property-based testing to check that the scoring and the bowling game sort of worked. And it would be difficult to generate enough examples in that case to test that it worked in all cases, but throwing random things at it and saying, well, if we've had enough turns, then the game should be over, for example, or that once somebody's rolled twice, it's definitely the next person's turn. Those are things that we can specify our properties of our system and then ask property-based testing to try and disprove them effectively.
You mentioned that you recently talked about property-based testing, which, led to this conversation in a way. Where are you employing or deploying property-based testing, and what kind of libraries are you using at the moment?
So I'm a developer largely in Kotlin these days, which is a library. Well, it's a language on the Java virtual machine. And we have a couple of options, but the one I've been using is called jQuick. The quick is quick as in quick check, although it's KW, just to be annoying, I think. Yeah. The developer of that seems to be very talented, very responsive, and he's done certainly a jolly good job of integrating with the test runners that we see on the JVM and finding ways where we can, I guess, have expressive tests, where we can read the tests and understand what they do as Java developers or Kotlin developers.
There are a few links that explain what property-based testing is in more detail, and I included them in the episode notes as usual. A good description comes from the original library, QuickCheck in Haskell itself. And another definition is from David McGregor, the author of the Hypothesis Python library, who wrote in 2016 that, and I quote, property-based testing is the construction of tests such that when these tests are fuzzed, failures in the test reveal problems with the system that could not have been revealed by direct fuzzing of that system. And if you're wondering what fuzzing is, well, here's David McGregor again. It's feeding a piece of code data from a large corpus, possibly dynamically generated, possibly dependent on the result of execution on previous data, in order to see whether it fails. Well, maybe that sounds a little bit too abstract right now, so let's talk about an example to make this a bit more concrete. Duncan already gave us a simple example with a function that returns the length of a string, which he admits is not particularly interesting, so let's choose another example. Let's say you want to do a round-trip test of decoding a string in JSON format into an object and then encoding it back into a JSON string. Your assumption and hope is that the de- and encoded JSON string has the same value as the original one. You could use unit tests for that, of course, but you would have to provide enough examples to be sure that your coding and decoding algorithm holds in a variety of different cases, which means you need to provide enough examples to make sure your JSON coder and decoder doesn't stumble over so-called edge cases. Well, the chances are you forgot one of those edge cases, which is even more likely the more complex your code gets. And this, of course, is where property-based testing comes in. With a few lines of code, you can focus on the data used in your test function. Behind the scenes, the property test function generates a set of tests with some randomly generated example data. So rather than specifying a set of data yourself, you let the property testing library check a range of different values for you, or fuzz the data, as David McGregor said. In addition to that, property testing is using a method called shrinking to make the tests even more efficient and narrow down where the failures really are. Shrinking may take some time to get your head around, as it did for me, to be honest. In principle, it works like this. Let's say your property-based test runs your test code 200 times with randomly generated data. And of the 200 runs, only 2 fail. So what you can do is to shrink, that is, to reduce the number of data that will not lead to the failure. In short, shrinking is the process of reducing your dataset under the condition that the tests will continue to fail at the same points. How all of that is implemented and how it works depends on the property testing library you're using. In the online ByteSized RSE class given by Jeremy Cohen and Stuart Kraut, Hypothesis, the library created by David McGregor, was used. And that's what I'm going to talk about next. Which also leads me to my next interview with Nicholas de Grosso, who's been using Hypothesis. Nicholas, who works for the University of Bonn, as he will explain in a second, responded to a call I made on social media, and I'm very, very grateful for his time. And so, here he is.
Hi, my name is Nick Del Grosso. I'm the group leader for a group at the University of Bonn called iBots, the iBehave Open Technology Support Group. We are a teaching RSE group that offers a lot of workshops for neuroscience researchers, and we offer consulting and coaching for researchers, mostly people who are either new in their PhD. They want to invest in skills that are going to carry them throughout their long projects, so that way they can continue to be productive. Or for people who have found that they are really invested in these technology and software skills, who want to take their work a step further and maybe open their career options up a little bit more.
Okay, thanks very much. So, Hypothesis, how did you get started into it, and what made you choose Hypothesis in the first place?
Well, I was one of those PhD students who wanted to open up my careers a little bit more. And so in the last year of my PhD or two, I started taking testing very seriously because I found myself rewriting software, realizing, I wasn't doing exactly what I wanted it to do. And I wanted to build something that was reliable for other people. I also found myself supervising people and collaborating with people. And whenever it came to people making contributions, I always wanted to say, yes, this is a great contribution. This is nice. But it took me a lot of time to evaluate whether something was good or not. And I found that the more automated tests I added to my software, the more I could say, yes, this is great. Thank you. So testing has been a really positive part of my life. I came across Hypothesis at an RSE conference. Well, it wasn't called RSE back then, but it was a scientific software section of a neuroscience conference. And someone was introducing Hypothesis in a talk. And when I took it home and started to apply it to my work, everything started to fail. I started to realize that my software, I had bugs in my software that I hadn't considered. Nowadays, we've got these AI co-pilot type things that are like pairing buddies who can help you make suggestions while you're working. And that was the first kind of testing buddy I ever had. Hypothesis suggested, hey, have you thought about this? Hey, did you consider that? And my code started to get a lot better.
You mentioned that you used testing before you used Hypothesis, so I guess you're referring to something like unit testing.
That's correct.
So what, in addition to the unit testing, did Hypothesis then bring to the table? So how is that different, in other words?
Well, what Hypothesis does is suggest inputs for your test functions. And this fit into my workflow for unit testing in a very nice way. I'd always start with some basic unit tests. And then as I started thinking of more and more test cases, I would start to use the parameterization features of my testing library. For example, PyTest has a parameterized decorator that's very helpful in Python. And eventually I'd start getting, 5, 10, 15 test cases. And I'd start to go, well, surely I must have thought of everything by now. And Hypothesis became that last bit, that last part that said, okay, have you really though? And usually it forced me to think about what I was really testing for on a much fine-grained level, and it gave me a lot more confidence. And more than that, it started making those test code for the code I really, really wanted to rely on, especially those utility functions, those low-level support functions. It just made them very strong without having a lot of test code burden.
How do you use Hypothesis then today?
Today, I use Hypothesis to support unit tests the same way as I started to before. Now, Hypothesis is much more powerful than that. It's based on an area of testing called property testing, which is not focused on testing exact outputs of a function, It's focused on aspects of a function. For example, if you're doing something with a table or data frame, you might want to say, okay, no matter what the inputs are, I want to make sure that a certain column gets created or a table gets created, or I want to make sure that the result is never none or something like that. Property testing is really good for that, for being able to give you that confidence that those things you think are true about the behavior of your function, of your code, are true. In research code, though, it's very rare for projects to reach the scale at which a property testing becomes, absolutely essential. Usually the projects start out as having a single user, which is the same person as the developer, and then maybe scaling up to having one other user and slowly getting up to that point. Yeah. This is partly due to the way that research is funded, how it's organized. So what property testing becomes really valuable for in research, as that I've seen, is when someone wants to publish a library as a methods paper, because it gives you that last little bit of confidence about what you can say in the methods paper that software does without increasing the amount of maintenance burden you're going to have after you start getting a lot of users from when the paper is published. So usually I introduce hypothesis to researchers right when they're at that stage, when they're saying, okay, we're going to do one last redesign. We know we want this paper. We have an idea of what the scope of this project is, and we know that the users are going to increase a little bit, but we don't want to have to rewrite this thing right after we publish it because we want to go to the next project. So we say, okay, let's do that one last little testing round. And that's usually where this goes.
When was this conference, by the way, the one that actually brought you to Hypothesis?
Oh, gosh. That must have been 7-8 years ago, a long time ago.
Oh, nice.
Hypothesis has been around for a while, and it's really matured as a library. If it has any issues, it's always with like the newest features, the most advanced use cases. Just going through the first getting started, you can get a lot of use out of it without having to learn every little feature.
If you could highlight perhaps for the users the kind of tips you have for them to use Hypothesis. Well, first of all, how would they get started with it? And then are there particular tricks that you found on the way that could help you with your hypothesis testing?
Well, getting started with Hypothesis is as simple as adding, if you're using PyTest, for example, which is probably the most popular testing library in Python, is using their given decorator that they supply, and specifying what inputs you want to parameterize over. It's usually a single line on top of one of your unit tests. And that's all you really need. The way I would recommend people start out with that is to go through that process of first not using Hypothesis, using some basic unit tests, parameterizing them a little bit. And then before you go on to write another function and keep building, add a Hypothesis property test either on top of it or see if you can replace it with Hypothesis test. One of two things usually happens when you do that. Either you find that your testing strategy was very good, but there were some cases you forgot. So that's very easy to add in. Or you find that when you're rewriting your test to be in this property testing way, you end up rewriting your test code ends up having exactly the same code as your source code. For example, you might write an add function. You might test at first. You say, okay, if I give in 3 and 2, does the result 5? And then you might do it again with some others. You might have 10 different cases with 10 different sets of numbers that add up. You might run a hypothesis and realize, oh, I forgot negative numbers. Oh, what if someone gives an infinite number? What if someone gives a NumPy array or something? What would that do? So that's all very nice. But the problem is when you add a hypothesis test to something like this, what you would find is that your test code will say, assert A plus B is equal to C. And that's exactly what your source code will say. When that happens, it turns out you're not really testing that much. And seeing that happen to your test code is a really good sign that you might not have been testing in a sustainable way. And that might give you ideas for more specific things to test for that won't get you in trouble in the future.
As Nicholas said, it's fairly easy to get started with Hypothesis. You install it simply with a pip install Hypothesis. One key element to using Hypothesis is the so-called strategies package within the library. Strategies is where the data generation happens. So you would expect strategies, that is generators, for basic types such as floating numbers, integers, characters and booleans. And indeed there are. They are part of the core strategies that Hypothesis provides. There are extended strategies like provisional and composite ones, not to mention custom generators, but let's not go into that right now. The other important element is, as Nicholas pointed out, the given decorator. The given decorator for your unit test function specifies which of the strategies apply to the function and to the data therein, Let's say your unit test asserts that some floating point operations return a certain value, so you have to import a floats strategy, which you would use in the given decorator as an argument. The hypothesis documentation has more examples of how that looks in practice. Another helpful feature of hypothesis is its example database, and this is where information about your test failures end up in. Hypothesis is rerunning those examples in your next test runs, and this helps you to check whether your bug fixes actually work. Hypothesis also allows you to specify test example data you want to be included in every run of your test function. There are, of course, plenty of other features in Hypothesis, but the ones I have just mentioned should be enough to get you started. And again, I encourage you to go and check the Hypothesis documentation, which is quite extensive. There is also more in-depth documentation covering the inner workings of Hypothesis. For instance, how David McGregor implemented shrinking in the library, which he says is somewhat different to the route others have taken. It makes some interesting, rather dense reading, so if you're interested, check out the links in the episode notes. And now, it's time for our quiz. And the two questions for this episode are: what is the difference between unit testing and property-based testing? And the second question is, using Hypothesis library, what does the example decorator do and why would you want to use it? Have a think, and if you like to send in your answers, email me on codeforthought@proton.me and you'll find the email address in the episode notes. And now for the two quiz questions from the last bite-sized episode on the citation file format. The first question was, apart from the CFF init, what other tools are available to manage citation file formats? Well, the most prominent tool is probably CFF convert, which allows you to, for example, validate your CFF file. The second question was, what are the key differences between citing software and citing articles? And the answer to that is that a published article is pretty much a finished and fixed product. The text and content, the list of authors, and the references don't change. With software, on the other hand, almost all of these things change more or less all the time. You get different contributors, the source code changes, and sometimes the direction and the whole architecture of the software itself changes as well. So there you have it, and good luck with the quiz questions of this episode. Thank you for listening to this episode of Code for Thought Bite-Sized. The content and the interactive bite-sized RSE sessions are created and run by Jeremy Cohen from Imperial College London and Steve Crouch from Southampton University. The podcast episodes are produced by Peter Schmidt. Finally, we'd like to thank Universe HPC for their continuous support. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.